Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to picture something for a second. Think about the sheer kinetic reality of a major asteroid impact.
Oh, yeah, it's almost impossible to truly visualize.
Right, because we're talking about a mass of rock and iron, maybe 100 meters across, hitting the upper atmosphere at hypersonic speeds.
We're talking 20 to 30 kilometers per second.
Exactly. And at those velocities, the atmosphere doesn't just part for the rock. It compresses so violently that the air itself turns into this superheated plasma.
Which is terrifying, honestly.
It is. And when that mass finally strikes the continental crust, the physics just completely defy our normal terrestrial frames of reference.
The pressure is so high it exceeds the structural integrity of any known mineral on Earth.
Right. Solid bedrock doesn't just crack or fracture. It behaves like a fluid. It melts.
A huge portion of it literally vaporizes into a localized atmospheric plume right on impact.
And then you have this massive shockwave that spreads outward, just instantly leveling all the topography.
While underneath, a superheated melt sheet is forged in literal milliseconds.
It's the ultimate sterilization event, right? I mean, the thermal radiation alone should eradicate any complex organic chemistry for miles and miles.
That has always been the standard assumption.
Our whole traditional understanding of astrobiology kind of frames these impacts as hard reset buttons.
Yeah.
Like they are the great terminators of life.
But what if that interpretation is just fundamentally backward?
Well, exactly. What if the intense thermal energy and the extreme pressure of an asteroid impact don't just leave a sterile geological scar?
What if they actually synthesize the exact thermodynamic and chemical conditions needed to incubate life
in a world that is otherwise completely hostile to it?
The paradigm in the scientific community is definitely shifting in that direction right now.
Okay, let's unpack this because it's a massive shift.
For decades, we've categorized impact craters strictly through this lens of catastrophic destruction.
Mainly because the visible macro-level effects are just so incredibly severe.
Right. But when you shift the scale and you examine the post-impact environment geologically over tens of thousands of years, the narrative totally inverts.
The extreme violence is actually what generates the long-term energy gradient you need to drive complex biogeochemical cycles.
Exactly. Destruction and creation become two ends of the exact same thermodynamic process.
So today we are exploring a really groundbreaking discovery from South Korea that links these violent impacts to the very oxygen we breathe.
And this earthly revelation is frankly acting like a treasure map for finding life on Mars, too.
Yeah, it's wild. The research comes from a team at the Korea Institute of Geoscience and Mineral Resources, led by Dr. Jae-soo Lim.
They've given us a completely new framework for understanding the aftermath of cosmic impacts.
Let's ground this geographically first because the location is super important. We're talking about the Hapcheon impact crater,
which is located in the Joseon-Chogi Basin.
Right, and this basin is a really distinct bowl-shaped depression on the Korean peninsula.
And what's fascinating is that it's the only confirmed impact crater on the entire peninsula.
Which is crazy when you think about it. It's a massive 7-kilometer wide structure.
But it was only definitively confirmed as an impact crater back in 2021.
How does a 7-kilometer crater stay hidden until 2021?
Well, it's a testament to how dynamic Earth's surface really is.
Unlike the moon, right? Where craters just sit there perfectly preserved in a vacuum forever.
Exactly. Earth has a very active hydrological cycle. We have tectonic movement, heavy biological weathering.
And the Korean peninsula gets a lot of rainfall. Plus, it has incredibly dense vegetation.
Which is basically the perfect camouflage for geological anomalies.
So for decades, scientists just cataloged this basin as a structurally unusual valley.
Yeah, it took extensive subsurface drilling to figure it out. They had to look for microscopic evidence.
The shocked quartz, right?
Precisely.
Yes.
Shocked quartz only forms under the extreme instantaneous pressures of a bolide impact.
So finding that finally proved its extraterrestrial origin.
But that 2021 confirmation just laid the groundwork. The real bombshell is the 2026 update.
Right. Dr. Lim's team focused on the northwestern sector of the crater, a spot they called Site STR.
And what they found there just completely recontextualized the whole basin.
They discovered ancient microbial structures called stromatolites.
Just sitting right there in the crater.
Wait, let me stop you there. because common sense is screaming at me right now.
I know exactly what we're going to ask.
If an asteroid vaporizes rock and creates this massive, superheated, sterile crater, how do delicate microbial structures just appear there?
It seems like a total paradox.
Right. How does a zone of absolute multi-megaton annihilation become a biological nursery?
It's a great question. And if you look at the immediate seconds or days or even years after the impact, you're totally right.
It's just a floor of molten glass and shocked rock.
Utterly sterile. But the biological incubation doesn't happen concurrently with the impact.
Ah, okay, so there's a timeline here.
Exactly. We have to introduce the concept of a post-impact hydrothermal lacustrine environment.
Hydrothermal lakes. Let's trace the thermodynamics of that.
So the kinetic energy of the impact melts the bedrock, creating this subterranean layer of superheated rock.
The melt sheet.
Yes. And because this melt sheet is buried under hundreds of feet of fractured rock and insulating breccia, it cools down incredibly slowly.
It basically acts like a giant subterranean furnace.
A thermal blanket, yes. And then, over centuries, the climate stabilizes.
Rainwater and groundwater start to fill the crater basin.
Right. And as that water percolates down through the highly fractured rock, it hits the residual heat of the melt sheet.
It gets superheated and rises back to the surface.
Through convection, exactly. This creates a closed-loop hydrothermal system.
Wow. So it's not just a warm bottle.
No, as the water circulates through all that pulverized bedrock, the heat dramatically accelerates the dissolution of minerals.
The crater lake becomes a highly concentrated chemical reservoir.
Enriched with iron, silica, all these essential trace elements.
So the initial violence is actually necessary. It shatters the bedrock, which increases the surface area for the water to interact with.
And the sustained heat turns the whole basin into a highly efficient chemical solvent.
It's literally a self-sustaining hydrothermal bioreactor.
That's the precise dynamic.
Yeah.
And within this stable, warm, nutrient-rich spa, essentially, life thrives.
Specifically, the cyanobacteria that built those stromatolites at Site STR.
Let's actually talk about what stromatolites are, because they're fascinating.
Oh, definitely. I like to avoid heavy jargon, so I always think of them as ancient layered apartment buildings.
That's actually a fantastic analogy.
Built by microscopic tenants, the cyanobacteria.
Right, and these cyanobacteria are photosynthetic. They eat sunlight and exhale oxygen.
And they have a fossil record that dates back, 3.5 billion years?
Roughly, yes. They're some of the oldest known life forms on the planet.
So how do they actually build these structures?
Well, as a colony of cyanobacteria grows, they precipitate calcium carbonate as a byproduct of their metabolism.
And as they do that, they trap ambient sediment from the water.
Exactly. So they precipitate minerals and trap sediment, building these structures up layer by microscopic layer over very long periods.
Which means they aren't just fossilized microbes. They're basically biogeochemical chronometers.
They are literal history books made of rock.
Because every layer traps the chemical signature of the lake at the exact moment that specific layer formed.
Like biological tree rings.
Yeah. I kind of picture them like a layered jawbreaker candy.
And the KIGAM team didn't just look at the outside of the jawbreaker. They sliced it open and analyzed the layers.
They performed really granular geochemical analyses across the cross-sections of these 10 to 20 centimeter structures.
And we have to note the temporal markers here because the Hapcheon crater is relatively young geologically.
Right. It's from the late Pleistocene epoch, about 50,000 years ago.
Which is perfect for this kind of study.
Because 50,000 years is well within the range for radiocarbon dating.
Specifically, carbon-14 analysis, yes.
Carbon-14 has a half-life of around 5,730 years, right?
Exactly. So it's useless for dating billion-year-old dinosaur bones, but it's incredible for higher-resolution, absolute dating of the late Pleistocene.
So they anchored the timeline using 14C and then mapped the isotopic variations across the jawbreaker layers.
Tracking the changing conditions of the lake from the inner core of the stromatolite all the way out to its surface.
And the data from that isotopic gradient is basically the smoking gun for this whole hydrothermal theory.
The signature is definitive. They looked at the ratios of stable isotopes, like oxygen-18 to oxygen-16, within those carbonate layers.
And they found a massive thermal gradient.
The inner layers, the oldest parts that formed first, had ratios corresponding to significantly elevated water temperatures.
Proving that they formed in a highly active hydrothermal environment.
And then, as you measure outward toward the younger layers of the jawbreaker,
the ratios shift to show progressively cooler water.
Yes. What's fascinating here is this proves the structures began growing during the hottest, earliest phase of the newly formed lake.
And they just kept growing as that subterranean melt sheet slowly ran out of juice over thousands of years.
Until the hydrothermal spa eventually cooled down into a standard ambient temperature lake.
They captured the entire thermodynamic life cycle of the impact's aftermath. That is incredible.
But wait, it gets better.
Oh, lay it on me.
The analysis showed that these microbial colonies were actually incorporating extraterrestrial material into their structures.
Wait, really? Remnants of the asteroid itself?
Yes. They mixed material from the impactor with the violently altered local bedrock.
So they were literally metabolizing and building their homes out of the fractured weapon that tried to destroy their environment.
It's the ultimate display of biological resourcefulness.
The asteroid delivered the heat, but its pulverized remains also provided the exact trace minerals they needed to accelerate their growth.
Things like phosphorus and specific iron isotopes.
Okay, this forces a massive logical leap for me.
I think I know where you're going with this.
If a local asteroid impact in South Korea 50,000 years ago can create a perfect self-sustaining incubator for cyanobacteria.
We have to scale this up to the entire planet billions of years ago.
Exactly. We have to talk about the Archean eon, roughly 2.4 billion years ago.
The lead up to the Great Oxidation Event, or the GOE.
Because if we connect this to the bigger picture, Earth back then was completely alien.
It was fundamentally hostile to complex life.
The atmosphere had zero free oxygen. It was this toxic soup of methane, ammonia, and carbon dioxide.
And the global oceans were largely anoxic and highly enriched in dissolved iron.
So if a primitive cyanobacteria colony tried to evolve and photosynthesize out in the open ocean, it was basically doomed.
It faced an incredibly uphill battle.
Because any free oxygen they produced would instantly bond with the ambient dissolved iron, right?
Yes, it would scavenge the oxygen and precipitate out as iron oxide.
Plus, there was no ozone layer yet.
So the surface of the ocean was being continuously bombarded by lethal levels of ultraviolet radiation.
The open ocean was a chemical sink and a radiation death trap.
So the long-standing mystery has always been, how did cyanobacteria ever establish a large enough population to overcome all that?
How did they eventually off-gas enough oxygen to permanently alter the atmosphere?
This is exactly where Dr. Lim's team points to the concept of the oxygen oasis.
And the Hapcheon crater provides the physical blueprint for it.
Think about the Archean eon. The Earth was experiencing a vastly higher rate of asteroid bombardment back then.
The crust was just being repeatedly shattered by space rocks.
And instead of seeing that as a series of extinction events, this hydrothermal model suggests something totally different.
Every single impact was basically excavating a biologically optimized safe haven.
A crater lake offers massive advantages over the open ocean on early Earth.
Well, first off, the rim of the crater physically isolates the lake from the global ocean.
Right. It acts as a barrier against those turbulent, iron-rich currents, stopping the immediate scavenging of the new oxygen.
And second, that hydrothermal circulation provides a constant upwelling of nutrients, right?
Completely independent of the nutrient-starved surface waters of the global ocean.
And third, the physical depth of a crater lake gives you a thick collar of water,
which attenuates and blocks that lethal UV radiation from the sun,
allowing the cyanobacteria to safely photosynthesize in the Fertic zone.
So within these isolated, thermally regulated impact basins, the cyanobacteria population could just absolutely boom.
Because it's localized, the oxygen they make eventually outpaces the chemical sinks in the crater.
And the lake becomes completely saturated with free oxygen.
So are we saying that before the entire atmosphere became breathable, life was essentially sheltering in these scattered, asteroid-made safe havens?
That is exactly what the data suggests.
Were these craters literally the localized engines that tipped the scales for the whole planet?
Yes. Once the local water column in a crater reached saturation, all that excess oxygen had nowhere to go but up.
It would bubble up and off-gas into the sky.
So the planetary scale transition of the Great Oxidation Event probably didn't happen uniformly across the ocean.
It was driven by a decentralized network of millions of these hydrothermal crater lakes.
All of them steadily pumping oxygen into the toxic Archean sky.
Wow. The cosmic bombardment was literally terraforming the planet.
It provided the isolated high-energy sanctuaries that life required to achieve critical mass.
The very mechanism we assumed suppressed early life was actually its greatest catalyst.
It beautifully resolves a major thermodynamic paradox in evolutionary biology.
Because major biological transitions require immense amounts of energy, right?
And highly specific, stable chemical gradients.
Which a post-impact environment provides perfectly. a massive spike of kinetic energy converted into a slow-release thermal gradient.
Driving a localized chemical cycle for thousands and thousands of years.
Okay, here's where it gets really interesting.
Let's take it off-world.
Exactly. If this mechanism drove early life on Earth, we can't just limit this to our own biosphere.
No, this terrestrial analog instantly becomes the ultimate diagnostic tool for astrobiology.
Especially when we look at the planetary history of Mars.
When you look at the Noachian period of Mars, which is roughly the same time as Earth's Archean eon, the similarities are striking.
Mars had a thicker atmosphere back then. It had abundant surface water.
And it was getting hammered by the exact same heavy bombardment of asteroids that Earth was.
Its surface is still completely scarred with those ancient basins.
But unlike Earth, where plate tectonics and biological erosion have wiped our early crater history, clean Mars essentially froze in place.
So the ancient paleolakes of Mars are just sitting there, structurally intact.
Which raises an important question. If impact craters on Earth were the incubators for microbial life,
then the dormant craters on Mars aren't just geological depressions.
they are the fossilized remains of potential alien nurseries.
And the Hapcheon crater research totally alters how we investigate them.
Because until now, looking for life on Mars has been like searching for a microscopic needle in a planetary haystack.
We know water was there, so we send rovers to ancient lake beds, like the Jezero crater.
But just knowing a basin once held water isn't enough.
We need to know what specifically to look for, and the Hapcheon stromatolites provide a literal treasure map.
They give us the precise isotopic fingerprint of impact-driven hydrothermal biology.
It's like a calibration tool for our rovers.
Exactly. Think about NASA's Perseverance rover driving around the Jezero crater right now.
Jezero is an ancient impact basin that hosted a paleo lake, right?
Yes. And Perseverance has highly advanced spectroscopy instruments.
Like PI6L, which maps the elemental composition of rocks at a sub-millimeter scale.
And Sherlock, which scans for organic compounds and specific minerals.
But all that data requires a reference point.
Right. If Perseverance finds a carbonate layer in the Jezero Basin, the Hapcheon study tells scientists the exact isotopic ratios of carbon and oxygen to look for,
To determine if it formed in a hot, cooling hydrothermal gradient.
Furthermore, the South Korean data tells them to look for extraterrestrial trace minerals bound within the rock.
Like those specific isotopes of strontium, or the Schox quartz we talked about earlier, mixed right into the carbonate matrix.
We aren't just blindly looking for vague signs of past water anymore.
We know exactly what chemical fingerprints to look for when the rover scrapes the dirt.
We have the exact terrestrial reference spectrum for what a microbial oasis looks like.
We've basically transitioned from blind exploration to highly targeted forensic geology.
It's a beautiful illustration of uniformitarianism in geology, but on an interplanetary scale.
Meaning the physics that govern a crater in South Korea are the same ones that operated on ancient Mars.
The fundamental laws of thermodynamics and geochemistry don't change just because you're on another planet.
By rigorously studying this earthly discovery, we unlock the code to hunt for astrobiology across the solar system.
It's incredibly powerful.
Let's bring all these threads together because the sheer scope of this is staggering.
It really is a massive shift in perspective.
We start with a catastrophic event, a meteorite strike that melts the crust and sterilizes the landscape.
But beneath the destruction, a massive reservoir of heat is trapped in the melt sheet.
As water returns, that trapped heat drives a long-term, highly active mineral bath,
turning a crater into a nutrient-rich, protected bioreactor.
where microscopic cyanobacteria can thrive, utilizing the minerals from the very asteroid that made the crater.
They build their stromatolite structures, locking the thermal history of the lake into stone.
And on early Earth, millions of these isolated oases pumped out oxygen until they literally changed the atmosphere of our planet.
The violence of the cosmos provided the scaffolding for aerobic life to dominate.
And now, the chemical clues left behind in South Korea are guiding our rovers on Mars, telling them exactly where to look for alien biology.
It completely reframes our relationship with destructive cosmic phenomena.
It does. It shows that complex biological systems require immense energy, and early on, that energy is delivered through catastrophic impacts.
Destruction isn't an anomaly. It's a prerequisite step in chemical evolution.
The next time you take a deep breath of oxygen, I want you to remember this.
You owe a tiny fraction of that life-giving gas to the cosmic violence of ancient asteroid impacts.
The biological comfort we enjoy today is the downstream consequence of a terrifying era of planetary bombardment.
We are literally breathing the biological dividends of falling stars.
Which prompts a really provocative final thought for you to ponder.
Oh, I'm curious where you're taking this.
Well, if life on Earth utilized the chaotic destruction of asteroid impacts to build oxygen oases and terraform the planet.
What other catastrophic events in the universe are doing the same thing?
Exactly. What other seemingly destructive cosmic phenomena, like the intense radiation of a nearby supernova or the tidal friction of massive gas giants tearing a moon apart, are happening right now, secretly planting the seeds for entirely new forms of life?